In this video, I'm going to start the review outline for test number 3. So the units have already been filled out, so be sure that you are familiar with all the units for all of the different variables. And we'll go ahead and start with chapter 21. So we'll start with some conceptual ideas here. So what's the similarities and differences between electric charges and magnetic poles? So the similarity is that both of the like charges and the like poles will repel, right? If you have two positive charges, they'll repel because they're like charges. If you have two like poles, so let's say you've got a north and a south here, and you've got a south and a north here, they're like poles. That means these will repel each other, and opposite charges and opposite poles attract. The other conceptual thing is that electric charges can be isolated. You can have a positive charge separated from a negative charge, a proton separated from an electron, but magnetic poles cannot. So what this means is that if you have a magnet that has a north and south pole and now you're cutting it in half, then you're actually going to be left with two magnets now. And each one will still have a north and a south. So it's not possible to get a south by itself or a north by itself. And then the first topic here that relates to an equation is finding the field due to a straight current carrying wire. So this is talking about the first equation right here. And this equation tells us that if we have a current in a wire, then this gives us the field at a certain distance r away. So that means at this distance r, there's going to be a field. But if r gets further away, then the field will get weaker. So you need to be able to calculate that field due to one or more wires. So let's say that I had two wires. Then this one would produce a field, let's say at this location here. But this wire would also produce a field at this location. So you would calculate each of them separately, and then you're going to add or subtract them depending which way they're going. And the right-hand rule is going to tell us which way is that field going. So you want to put your thumb in the direction of the current, and the fingers will curl in the direction of the field. So this is hard to draw, but if you have your thumb up, then your fingers, they're going behind here, and they're coming to the front here. You've got 4 fingers here, got your thumb. So this is the best I can do as far as a picture. But you see how the fingers are curling behind the thumb, and then here they're going in front of the thumb. The thumb is the current. So what this means is that the field is making a loop around the wire, and the loop is going behind the wire here. It's going in front of the wire here. So based on that, you need to be able to know which way the field is going. So if you're to the left of the wire, you see that your fingers are coming toward you. That means the field is going out of the page. We use a dot. If you are to the right of the wire, you see there the fingers are going in, or if you curl your fingers, if you had super long fingers you could curl over, they would be going into the page here. So you would put an X to say the field is going into the page anywhere to the right. And so if you had another wire here, you'd have to do the same thing. The field would be going out of the page if you're anywhere to the left. It would be going into the page if you're anywhere to the right of the wire. So if you need to find, well, what's the field at a certain location, let's say right here in the center, at this point, well, this wire created a field into the page, this wire created a field out of the page, so that means the two fields would subtract. They're not going to necessarily cancel out. It depends how strong the field is, and that comes from the first equation that we talked about right here. The current is going to the right. That means that the field is going out of the page above and into the page below. You can use that same right-hand rule. And you also want to be able to calculate this if the current is coming, let's say, out of the page or into the page, right? If the current is going into the page, then now when you curl your fingers, then you should see your fingers curling this way. So that means that the magnetic field is making a clockwise loop when the current was going into the page. So that means that you need to be able to know, well, which way is that field going depending on where you are. So let me make that loop a little bit nicer here. So if you're right here, that means you're going up. If you're right here, you're going to the right. If you're to the right of the wire, you're going down. Now, if you're right here, diagonal, then you're going diagonal, right? The field is always going tangent or touching that circle.